an intense class, and this week is super intense, okay? So you have to stay with me. So last week was more of a process, and it was more of a sequential kind of process. But today we're talking about physics. And I'm going to go through not only one physics, but a number of physics. Thermal, electrostatics, elasticity. So hopefully you can stay with me. If you have any questions, let me know. In fact, it turns out this is one of the tough lectures because we introduced one concept which is called physics of scales. MEMS is a walk of scales. The reason why spiders walk on water, some extension which you back is no more negligible. So I'm going to cover that. So really, I would appreciate if you have questions, just ask. Because I'll guarantee you, I mean, based on the data that I have, it's kind of a little bit difficult. So the first part, physics of MEMS, essentially we'll be dealing with scaling of laws for force, and then force per energy, power. So it makes, some of the physics scale very well for forces, but eventually what matters is power density. So they may not scale very well with power density. So we'll talk about those, and we're going to go through the details. And I'll talk about micromechanics, more of elasticity, more of mechanics of material, not mechanics of material, but mechanics of solids, but in more generalized format. Electrostatics, by now, I've already hopefully made you brave enough not to fear anything of this sort. It's not a big deal. It's the same equation for temperature distribution. Del squared V is equal to 0. Del squared T is equal to 0. It's the same equation, so we shouldn't be afraid of that. And then heat transfer. Again, from the mathematics point of view, these two are very, very similar. Both of them are working on a scalar potential. One is temperature, the other one is voltage / potential. So the math is easy. The physics, then we'll try to relate that. Okay? All right, so, just to give you an introduction, why are we doing physics of MEMS, right? So each of the MEMS devices that we have work on a physics. And sometimes, of course, chemistry and all that kind of stuff, but typically they're driven by physics. Now, for example, let's talk about the easy one, which is a DNA chip. It comes in a variety of forms. One of them is for sequencing, then for aluminum. There's a company called Affymetrix in the Bay Area. So essentially what they're looking for is sequencing unknown genes for a specific disease. So we have markers for Parkinson's, markers for prostate and all that kind of stuff. So they specifically design for those. So they're not going to sequence all your genes, but they sequence only small. Part of that. Now, all this depends on physics. Okay, microfluidics, for example, electrostatics. In the case of alumina, it's mainly driven by diffusion, therefore it's microfluidics. There was a company called Nanogen. I used to work there, actually, a startup company. Eventually, the technology got sold to an Israeli company. But essentially, they were doing molecular diagnostics. But mainly for genetic diseases. So it got sold to an Israeli company. So in Israel, it turns out in every marriage, you need a gene counselor, genetic counselor. So our technology we had designed something called Ashkenazi panel, appropriate for that population. So anyway, the technology is amazing, it's still there. So it works with electrostatics. DNA has a charge, and we're moving DNA by applying a voltage, and we're able to collect within 15 minutes, 30 minutes. We will tell you, once we have your blood, of course, we process it, and then we'll tell you, okay, you're going to have susceptibility to this and that kind of disease. It doesn't mean you will produce that, but you have to. But some of them are like cystic fibrosis. You have it, you have it. You're going to develop that. But anyway, so microfluidics, heat transfer, mass transfer, electrostatics, and so on. Inkjet dispensers, inkjet printers. Now, 3D printers. In fact, 2 weeks ago, we had a faculty who was interviewing. We picked the other guy, but this guy was using actually microfluidics in terms of printing his polymer inside a liquid. So he could do a 3D, okay? As opposed to just building it, you know, one by one in a 2D fashion. So this consists of two-phase flow, thermodynamics, piezoresistivity, and all that kind of stuff. So if you don't understand this, then it becomes difficult to understand inkjet dispensers for 3D printing, the innovative ones, not the like the formula and all that. And this one we talked about it, micrometers in projectors. So you need to know a little bit of optics, refraction, reflection, diffraction, interferometry, and all that, and then mechanics and specific electrostatics. So that's the reason that why we're going to cover today. Okay, I mean today's kind of tough lecture. Okay, somebody was going to ask me, Omar.
Yeah, for the DNA, you say that you applied some voltage to make it move.
Yeah.
Approximately, what's the voltage that you were applying to it?
5 maximum.
5 maximum.
And I'll tell you the reason. What is what? Yeah, Arduino, for example, has a limit of 5 volts. So anything that's with the integrated circuits, they're limited with 5 volts.
So the limit is because of the Arduino capacity to high voltage? Or?
No, it's not. Well, yeah, integrated to the circuits, but I mean the DNA also gets fried. So you don't want to apply too much voltage. So you want to apply just a little. Okay, that's a good question. Okay, so what I would like to cover is so-called scaling in laws. Specifically, what we're going to look at is, you know, quantities like surface per volume or power per, power density and so on, okay? Now, typically, as you know, MEMS are extremely small, okay? The maximum range is within a millimeter range. The physics that you have neglected will not be neglected now, okay? So, so essentially it requires a neural intuition, stuff that you've been taught to neglect. For example, I think I was covering this in my finite element class, Navier-Stokes, fluid flow. The only, you know, pressure that you're looking at is just delta P, the external force. But I kept on giving the example of how many people have watched the movie The Hunt for Red October? Only 3 people? Alright, so you gotta watch that movie. So it's like, it's a submarine without any moving parts, so it doesn't make any noise. Of course it's a movie, but it was one of the, Sean Connery's one of well-known movies. Now, the deal is, if you want to use Navier-Stokes equation, you're not going to put delta P. So you have to create another force, I mean you have to put another force, which is the Lorentz force, which is a function of the magnetic field as well as the electrical field. Anyway, so the first thing I want you to know as I'm building the story, okay, I'm going to go through each of the forces like surface tension, electrostatics, and all that. So the thing I want you to know is this. So for example, when I'm talking about length, okay, so the most basic dimension is length. And I'm going to represent that as S, okay? Of course, if length is S, what's area? S squared, right? So again, I'm talking about just a dimension, generic dimension. Okay, and volume is of course S cubed, right? And then the other dimension I'm going to talk about is time, okay? Time is, well, it's not going to vary as much as the others, but we'll keep it in the discussion. Okay. Now, given this, let's look at, so I'm going to derive equations, so I want you to stay with me. So, let's say that I have a force vector, okay? And the force is going to be a function of either just length. So when I derived and then I put these things, I did not include everything. So that's why I'm writing some of the steps, the intermediary steps. Now, there are some forces which scale. Okay, there's a word. They scale directly just with the length. Okay? So those type of forces, I'm going to put just S. There are some forces which scale with the area. So you could say equivalent or really proportional, you know, whatever, okay? Or equal, it doesn't really matter. Now there are forces which scale with the volume. And then there are some forces which are which scale with actually s to the power 4, length to the power 4. Okay? Now, if force is this, define as s squared, s cubed, and s4. How about acceleration? Now let's look at other quantities. I want to use the same thing. So by the way, I could take s this way, and then if I invert it, f transpose, then it becomes just s squared, s cubed, s4, right? So that's the way I have it here. Okay, now, acceleration. How is force related to acceleration? F is equal to m times a, right? So, F is equal to m times a, therefore a is force divided by m. Okay, for force, we know it's given by s squared, s cubed, s4. How about mass? How does mass scale with dimension, with length? So, mass is kind of related to the volume, right? The amount of stuff, right? So, you could assume, and then you could look at it here, so A is equal to F over M. Now, F is represented by these vector, so S1, S2, S3, S4, that's why I'm putting as F, generic, divided by mass, which scales with S cubed, okay? So, you could argue, if you follow the derivation, because A is equal to F over M, which is the same as F times M inverse, right? And for F, I have S, this particular S, but I'm going to give it the superscript F, times S to the power minus 3. So are you guys with me on this? Okay, it's very basic right now. First, I just define my S, then I'm dividing it with mass. And mass is pretty much known, it's S cubed. Okay, if you do that, I need somebody to walk me through this. Any volunteer? So what's the first term? The acceleration corresponding to a force that scales only with length. So shouldn't that be S times S to the power minus 3? 1 minus 3, so that should be S minus 2, right? And that's what I have. Okay, how about the next one? So it scales with S squared, multiply with S minus 3, S minus 1, right? So I could do the same thing with the other one. I have S cubed, multiply S minus 3, then that's S0, and then the last one is S to the power of 1. Okay. Everybody with me so far? Not a big deal. But he is just following the argument. Okay, now, let's look at time. How does time scale with length? So if you're dropping stuff, remember in high school, a ball thrown freely from a certain height, how long will it take it? T is equal to square root of 2gh, if I remember correctly. Yeah, there it is. So time, 2 times g times the height, take the square root of that, then that gives you height, right? Now, 2d over a, how did I, okay, 2d, yeah, d is the depth, so g is, yeah, mass times acceleration, right? So you could put as m over f, so this is equal to square root of 2d times mass divided by f, and you take the square root. Okay, yeah, d is equal to 80 squared over 2, that's the formula. Now, if I substitute these guys, the number 2 is just a multiplier, so forget that, okay? Now, d is just a length, therefore the dimension is going to be s to the power 1. Mass we said mass scales with volume, so that's s cubed. So you have s to the power 1 times s cubed, and then f, we're divided by f, so it's going to be sf, but since you're taking it out because it's divided, then you get s to the power minus f. Okay? No complication here. Essentially what I'm doing is, I have the formula, and I gave you the formula, and we turn each of these magnitudes to the scale, to the appropriate scale. And if you do that, then it turns out time will scale in this format. Now, so let me write it out. One more. Well, okay. So time, I need to simplify this. So I have s to the power 1, s to the power 3. So that's already s to the power 4, right? So s to the power 4, yeah. So s to the power 4 times s to the power minus f over 2. Right? And then you're taking the square root. So if you take the square root, do you agree this becomes s squared?
Yeah.
And you agree this becomes f over 4?
Didn't you already take the square root on the first one? Because it's s to the negative f here, and if you distribute it, it'd be negative f over 2.
Yeah, so. Oh, yeah. Very good. Otherwise, I would have. Okay? Now, I come back to this guy. Remember, the reason why I'm putting this s to the power minus f2, because force has 4 variations. It's either s or s squared or s cubed or s to the power 4. So it's a vector. It's not a single value. Now, for the first one, corresponding to the first one, then it's going to be s squared times f is 1, so you have minus half. So it's going to be 2 minus half. Let me see if that's what I have. Yeah. Yeah. Which is 1.5. Remember, power rules, right? Everybody with me on this one? So let me write it down. So T. So for the for forces that scale with S, then time will scale with s to the power 1.5. Now we're just doing mathematics, okay? We'll come to the physical meaning. Now, how about when it's scaled, for forces that a force that scales with s squared, then all you have to do is 2 by 2 minus 1, 2 minus 1, 1, and s, right? That's what I have. S to the power 1, which is the same as s. Similarly, when it's 0, so so when it's 0, how do we get 0.5? S to the power 0, that's 1 minus 1 half. I forgot S to the power half, right? So 0, how's that? 0.5. So f is 0, so that's s to the power 0, that's 1. Yeah, it should be 2. I gotta check this. The last one, oh wait a minute, what's going on here? Oh, I'm sorry, s cubed. I messed up. So s to the power 3 is 3 over 2, that's minus half, 2 minus half. You get half, right? So I can remove. All right, the last one is 4. 4 divided by 2 minus 2, 2 2s, then it gives you s to the power 0. That's what I have. Okay, we're getting there. Time by itself is, yeah, it's okay, but it's not very useful. Acceleration by itself, good, but not useful. What I'm interested in is actually power per volume, the power density. I mean, A larger volume will give you a certain power. A smaller volume can give you a certain power. You can't compare both of them unless you actually scale it down by the volume. You divide by the volume. So what I'm going to do is I'm going to do P over V. Now first I have to find what P is. P, as you know, is work done per time, right? Power. So work is force times distance, F times D, divided by divided by T. Now, if I want to write P, so I skipped actually one thing over there. No, actually I have P over here. Yeah. So P is going to be F times. So F is this guy. So let me write it out for you because. So like I said, this is F times D divided by T, which is times T to the power minus 1. Okay? So we said F is defined by S to the power 0, S to the power 1, S to the power 1, S to the power 2, S to the power 3, and S to the power 4. Okay? D is just S. And T, we already found out somewhere here. So, but remember it's T to the power minus 1. So you just inverted that one. So we had 1.5, now it becomes S to the power minus 1/5. S to the power minus 1/2. No, minus 1.5. Essentially what I'm doing is I'm just copying. So you have S1, but I'm inverting it so it becomes S to the power minus 1. And the next one is S to the power minus 0.5 because I'm inverting it. And then S0, if you invert it, you just get S0. Then all you have to do is, so that's power, add all the powers. So 1 plus 1 minus 1.5, 0.5. 2 plus 1, 3 minus 2, S to the power 2. 3 plus 1, 4, minus 0.5, 3.5, then the last one, 4 plus 1 minus 0, that's 5. Okay, the last one, we're almost there. I'm looking at power density, so power divided by volume. You take this guy divided by volume, which is 3. So if you take 0.5, subtract 3 from that, you get S to the power minus 2.5. And S2 divided by S3 is S minus 1. And S0.5, S squared. Okay, this is where we need to pose. So, if you follow the argument deriving, this is not a big deal. But what's a big deal is what you find at the end. So, what it says is, for a force which just scales with length, there are some forces which just scale with length. Okay? If you're pulling a string, it's a linear force. It's just going to scale with the length. Okay? There are forces that are applied on an area, like electrostatics. I'm going to show you that. Those scale with S squared. Okay, now, if I have a force which scales just with the length, the power density scales with minus 2.5. Okay, what does that mean? Let me give you the interpretation, the math interpretation. So, I have a force which scales with S. If I take that force and, well, if I take that dimension, cut it by 2. Okay? I have a force applied in a linear fashion. Now, instead of S, I'm going to take half. Now, the power density actually scales with S to the power minus 2.5. So the power density is going to scale in that negative fashion. Minus 2.5. Does that make sense? I'll try it again. So, this tells me for a moment you can forget that force scales with all these combinations, okay? So for a moment, assume that the force is going to scale just with length. Now, you followed my argument the way I derived the P over V scaling, and we got some numbers, right? Minus 2.5, minus 1, 0.5, and s to the power 2. Now, what this means is, assume I started with an S, okay? And then I take that S, and if I divide it by 2, S over 2, okay? What's going to happen is the force is going to scale half. The force is just going to be half, right? I started F because F was directly proportional to S. S is half, therefore F is going to be half. But the power density is going to be S to the power of minus 2.5. Or it's going to be 1 over S to the power of 2.5. So it's going to reduce much faster. An order of magnitude, well, I actually, as a function of the power of 2.5, exponential. Now, if I assume S squared, if it turns out I have a force which scales with S squared, now remember, if I reduce the length by half, how much does the force reduce? By 4. To the power, you reduce by half, then it's going to be squared, so it's going to reduce by S to the power 2, to the S to the, S to the power 4. Okay. Now, but the power density actually reduces only S to the power minus 1, just by the inverse. It doesn't reduce by 4 times. Well, for example, if I cut by 3, then it would have been 8 times, right? If you reduce the length, the force will reduce by 8 times. But the power density is just the inverse. 1 over 3. It's not 1 over 8, it's 1 over 3, which is favorable. Okay, I don't know if you're paying attention. So 1 over 3 is much more favorable than 1 over 8. Okay, we're getting there. Now, imagine I have a force which scales to S to the power 4. Then the P over, so if it scales to S to the power 4, if I cut it by 2, if I cut my length by 2, the force will be reduced by 2 to the power 4 by 16, by a factor of 16. But the power density is cut only by 4, which is favorable. So as you go down, actually, it becomes favorable. Do you understand the argument here? So we're trying to make sense, okay, we say, okay, surface tension, okay, reduces. If I reduce the size of my domain, whatever domain it is, then will my force actually scale in a favorable way? Will it increase or will it decrease? So if you play in a systematic way, you could show that for some forces actually it increases, for some forces it decreases, the power density. Okay? Any questions? Yes, Will.
By power density, are you talking about like
POS.
like a lithium-ion battery has like the power density of the charge and its size?
Right. So power,
Yeah.
right? Whether it's thermal power or mechanical power. Mechanical power is F times D. Work is F times T. Mechanical power is F times D divided by T. So that's my power. Now the density becomes that power divided by the volume. The same thing with batteries.
Yeah.
So you calculate the power, you calculate the energy. I calculate the energy is power density.
Okay.
Yeah. Okay. Yes.
So this is pretty much why it shows that the gravitational and magnetic or static force.
I'm coming to that. I'm coming to that. But that's what we're trying to show. Some, which ones scale in a favorable way. Now, trust me, it has implications. Okay? Now, for example, I'll give you there was another question.
Yeah.
Yes.
I guess I'm just wondering, like this is all situationally based, like in a situation where force would scale to the power
That's
of
right.
that correlates to like a power density correlating to the power to
That's right. Yeah.
Okay.
So that's what I'm trying to show. In fact, it's right there.
Okay.
So some forces, like surface tension force, Okay? Yeah, the first one. So essentially scales with linear S. Some if you have electrostats, apply a voltage on a wire, that voltage distribution is going to scale just with a wire. Heat transfer through a wire, again scales with S. Now, pressure. Pressure is what force divided by A, right? Pressure scales, and your muscle force actually scales with S squared. It's not a linear, it's a function of the area. Because you don't have just one side of a muscle, right? Electrostatics, typical electrostatics, plate. The micrometers that you have over there, they scale with S squared, and I'm going to show you the math. Gravitational force, not surprisingly, with volume, S cubed, right? The larger the mass, the larger the weight. Well, the larger the mass, the gravitational attraction. Yeah, you think about the F is equal to half times the radius cubed, the distance cubed, or whatever. That formula. Magnetic force scales S to the power 4. Okay, now let me see if you guys are thinking before I build my story. So we said, with this guy, actually, I have to make a correction. When you reduced the dimension, this one went by minus 2.5 means actually it increased because it's a negative, right? So you reduced your length by half, force reduced by half, but the power density increased almost to the power of 3. So I need to make that correction. I made a mistake. Now, the other spectrum is right here, S squared. You reduce by half, the magnetic force actually reduces by to the power by 4. You reduce by 3, magnetic force reduces by 8. Now, I'm more interested in, for now, for example, electrostatic S squared and S4. So which one is more favorable for scaling, for a micro device? If you're building a company which does actuation, it does actuation, but there are two physics available to you. One is electrostatics, like this guy. The other one is magnetic, electromagnetic. Which one is preferable in terms of your energy balance or power density budget? Which one?
The energy bond?
Well, purely the energy budget. Good. Yeah, you're small, so as you're reducing, actually what's happening is the reduction with electrostatics, with electrostatics actually it increases. It's inverse. You reduce by 2, it increases by 2. In electromagnetics, you reduce by 2 the dimension, and the electromagnetic force actually reduces even faster. So back in 99 or 2000, actually the road company is doing switches for that time of 3G wireless communication. So there was a company which actuation was electromagnetic. And the majority of the companies, and I told you a company called Optical Micro Machines, which was in San Diego, and I've told you the story, that's the largest collection of very brilliant people I've ever seen in the city. So they were working on electrostatic. Okay, they reduce the electrostatic voltage high. And that's what you have this guy. That's why this guy would never define. If you come to E321, the projector hasn't been changed since I've been here, 14 years. And if you count the number of times it's operated, the lifespan is 5 to 10 billion times. So, the lesson is S to the power 1, S to the power 2 scale extremely well. S to the power 3, especially S to the power 4 scales extremely down.
The ones that scale poorly, can you eventually neglect those and just focus on the ones there?
Well, I mean, it derives what you want to do, what you're going to do, right? So, for example, if you want to actuate stuff, you want to move stuff, you have a choice. So am I going to move them by electrostatics or electromagnetics? So then that's going to derive your design decision. So that's why we're really looking at a very fundamental level, first principle level. And one of the reasons I've told you that last week I argued with, about this class is you deal with fundamentals. In a design process, at the beginning, when you make a decision, your decision has to be based on these guys. Without doing the fundamental, first principle, then you build a device and you're going to find out, your power density budget is terrible. That's the argument I'm trying to make here. Okay? Now, is everybody with me on this? Any questions? I'll spend some, whatever time is required on this. Now, if you understood this, let's look at why electrostatic force sometimes scales with s to the power 2. Why, and then sometimes s to the power of this. S to the power 1. And why does electromagnetic scale with s to the power 4? Okay? So, this is where we're going to look at the physics. Electrostatics. So essentially this summarizes what I was saying. For force laws with scaling higher than s to the power 2. Remember, s to the power 2 is electrostatic. That's a threshold. S to the power 3, s to the power 4 is electromagnetic. Anything greater than s squared, the power generated per unit volume degrades as the scale, and this is what this shows you. The load force plotted with the load dimension. So the volume forces actually degrade as you increase that. Okay? Well, actually, not nanoscale ones, in fact. So that's a key conclusion. Now, let's look at electrostatic force. Why does it scale with s squared? You guys remember 2 plates? The problem with 2 plates? Charge building, capacitors. Anybody heard of Maxwell? The company Maxwell? So the only company is Diego. Don't like that. Maxwell Technology. So essentially what they do is they build these capacitors. What's the thing about capacitors? They have energy storage, but batteries are energy storage. But why are capacitors sometimes better than batteries?
Well,
It's quick release.
They're like releasing energy, so that's why they're able to accelerate so quickly.
Releasing energy in a
Quick
fast,
release.
which is power density. So, for example, if you're operating a big bus, you want to accelerate on a huge mass. In fact, where they have big markets in buses, like they're huge. So because they often stop, they break and then they start. So if you want to start with your electrical motor, there's no way you're going to accelerate fast. Because the battery is going to deliver very, very slow. With capacitors, actually, they were going to down things very fast. Now, so, if you have 2 capacitors, 2 plates, separated by a distance delta, and you apply a voltage difference V, then the electrostatic force, you may remember this from high school, or if you have taken any 197 or I don't know, one of the courses, then the electrostatic force between these 2 plates, and I need you to remember this equation, is minus half times epsilon 0, which is the permittivity of the media, okay? Times, here I put as a derivative of WLD, so that's a volume, times E squared. Okay? Yeah. So let me square. So minus half epsilon 0 of d by dx of W, which is one of the dimensions, L, the length, D, the depth, so linear dimensions, times E squared, where E is the electric field. So FES typically F electrostatics is minus half times epsilon. I'm thinking of a simple AV divided by D if you simplify that, but let me see. this may end up confusing you. So let me keep it as a differential form, okay? Minus d by dx of w times L times d times e squared, okay? Now E, I need you to remember this. Electric field, it's not a big deal. I've been talking about this from day one, okay? Electric field is delta V divided by delta X. So if I have 2 points, this is V2 and V1 with a dimension of, with the coordinate X2 and X1, then this is V2 minus V1 divided by X2 minus X1. I come back to this again and again. In fact, ME 610 people, Simon, I thought I saw you, yeah. So I just give them the exam, but I like this concept, so I'm going to ask you this eventually. Okay. So, electric field is voltage gradient, delta V divided by delta X. Okay, so anyway, here I'm going to take a derivative. So if you simplify this, you're going to find out. So I have W, so that's S. This is another S. This is another S, right? But I'm differentiating this with respect to X. So one of the X's is going to go. One of the S's is going to go. So in terms of proportion, so this is dimensioning, that's going to be S squared. Okay? Now E squared, that's where it gets interesting. In fact, I have the formula for E. E is voltage over distance. So this is where you have to pay attention. So far, remember the way I built this subject so far. Very simple mathematics, but with the concept involved, right? Now that you followed me, or I think you followed me, I'm going to go to the equations. I'm going to go to the physics. So the first thing I'm going to throw on you is, here I'm going to take a derivative, right? D by dx of E squared. But I have to know first what E is. E is delta V divided by delta D. Okay? Now, it turns out voltage, and this is what you have to believe me, voltage will scale either with S to the power half, okay? Or it scales just with S, depending on the source. Okay? But that's not a big deal. I'm going to make a derivation for both of them. Now, if voltage scales with S to the power 0.5, then E is going to be V over D, 0.5 minus 1, that's going to give me minus 0.5, right? This guy, E, voltage is already S to the power 1, S is already S to the power 1, divided, then you're going to get 1, which is S to the power 0, right? So you get that. So, F is going to be S squared, just like the way I put it over here, times the dimension of E squared. So E is either S1,
Negative 0.5 or 0.
yeah, negative point, yeah, so, yeah, well, E is already 0.5, yeah. It's either S to the power minus 0.5 or S to the power 0 squared. So if you take this guy, then it's going to be S squared times E squared. Now E is 0.5, so if I square this minus 1, hold on. So S squared, so this should be, to get 1, then that should be minus 1, right? Yeah, okay. Minus 0.5 times 1, that's negative 1, so that should give you S to the power 1. And this is 0, so you're going to get S squared. So F is going to scale either S to the power 1 or it's going to scale S to the power 2. Yes?
Can you give like an example of, in one case where voltage might scale to like to the 1/2, or, just length and how we can tell the difference?
So,
Like which case you have, or
so remember, voltage is about a potential difference, right? So you get a potential difference based on charge. Now, if you have a linear distribution, hold that. So voltage, right? So it's a potential difference. So if you have a linear distribution, you get s to the power 1. Okay, it just varies with the length. Yeah, 0.5. That's where it gets a little bit weird. All right, I'll come back to the s to the power 0.5. But typically, it's a charge, linear charge distribution, then it's going to scale with the length. So remember, it's like temperature, right? How do you get temperature difference? So you have to have a heat source. If you don't have a heat source, then there is no temperature difference. Now, you could voltage the same thing. So if you could assume that the charge is distributed along a certain line, then it's going to scale with s to the power 1. So here is the point I want you to pay attention. So depending on our assumption, then you're going to have s to the power 1 or s to the power 2, right? And this goes back to what I said before. Remember scaling of forces? S to the power 1, it could be surface tension force, or it could be electrostatics. S to the power 2, also electrostatics. Now, typically, I'm going to ignore the s to the power minus. That's more of a theoretical interest. Okay? So, I want you to remember this. As far as electrostatics is concerned, I'm going to concentrate on s to the power 2. Okay? So, which means for the voltage, just a linear voltage distribution. Okay, before I move any questions so far? So, this is the first physics. I'm going to do 1 or 2 physics again. Electromagnetics. Then you're going to run away.
So why is E S
V over.
or no E
Yeah.
for why is that S to the power negative 5? Yeah.
Yeah, so we said E is V over D, right? Delta V by delta D. Voltage, as we were explaining, is either this guy or this guy. Let's take this guy. So you have S to the power 1. Then I divide by D, and D is of course S. S to the power 1 divided by S to the power 1, then you get S to the power 0.
Okay.
And you could do that, 0.5 minus 1 minus 0.
Okay. Then we apply that. We say okay. That makes sense. Okay.
Yeah. Then you multiply these two, then you get that. Now, I don't want you to, so this is what I want you to know. So the math was interesting for me. Freaking you out, I know that. But at the end, the reason why we did this is, if I have an electrode, in a couple of weeks you guys will be designing stuff. And if I have an electrode and I reduce its size by 100, by 10. Okay, I have an electrode, X, just one X size, not even Y. I reduce it by 10, the electrostatic force actually reduces by 100 because it squares with s to the power 2. However, the power density at the end, as engineers, this is what you have to talk. Really, the fact that the electrostatic force changed, reduced, of course it's expected. First you had a bigger electrode, now you have a smaller electrode, then the electrostatic force is not going to increase, even intuitively. However, the power density, how much power you're getting from that small volume has increased by 10. Isn't that very interesting? I mean, you reduce the emission, but the power density is increasing. I mean, that's a dream of every battery and energy storage unit, right? So, make sure you understand the implication, but also make sure you understand the physics, how we got it. You do that, then you are almost a perfect engineer. Okay? Of course, you will need ethics.
Things, I understand the arguments that you're telling.
Yeah.
Why do we want it in this way, matrices? Is in order for the computer to analyze all the data?
No,
or?
computer is not analyzing. I mean, we're talking about just Leonardo da Vinci. Just all here. You're sitting down, you're hanging out, and you're doing first principles. The reason I did it by 4 is because, as I showed you, because otherwise I have to do it 4 times. First I have to derive for s to the power 1, then I have to derive the whole thing s to the power 2. Already you're trying to run away and then 4. So that's why I put it in a matrix, I mean a vector form. It's an effective way of representing. Any other question? Okay. All right, you guys are doing fine. All right, let's see if you could handle it.
How you take the original equation and put it into like an S form is just by realizing from this equation.
This guy?
It's just from realizing that equation right there.
Yeah. I mean,
just
electrostatic
pull it.
forces given us this.
Because you know each one. and then-
Yeah.
I see. Okay.
Yeah.
So you have-
Electrostatics, first principles. Again, what I'm trying to emphasize to you guys is always about first principle. That's why, you are an engineer. I mean, every time you get confused, you always have to start from first principles. What is the common denominator that we agree on? Electrostatic force between 2 plates, we know that. The formula is given that way. Then from that, you derive.
Making the jump from width times length times the distance.
Yeah.
That's just S cubed, but since you have the D.
Then it becomes S squared.
Okay.
Yeah, because I'm taking a derivative. Yeah. Okay? All right, now let's talk about magnetics. Because I've been bad-mouthing magnetics for some time now, right? We said the power density, actually, you reduce the size, the power density is going to actually reduce even much faster. Why? Again, it's back to my, I remember my freshman, I took a basic electronics course, or electrical engineering course, and if you guys remember, when you have 2 wires, separated by some distance, and there is electric field in a certain direction, and it's going to have magnetic force in the 90 degree, and that's the whole basis of SE works, right? Kinetic current works. The actual Tesla guy spent all his life worrying about stuff like this, right? DC versus AC. So when you have 2 wires, one of them carrying a current IA, the other one carrying a current IB, and then length is L, but they are divided by a distance D. The magnetic force that's generated, okay, is the permittivity, mu0, divided by 2 pi, that's a constant, but more importantly, it's IA times IB, the product of the 2 currents, times their length divided by the distance. Again, first principles, because you were supposed to have covered this in high school or AP or whatever, or freshman physics, right? Everybody with me on this. Let's agree on that. It's the same way. Remember, with electrostatics, what I did was I went back to the first principle equation, then I just played with that and found out how it scales. Now, this guy, 2I terms. So, now that we're talking about dimensions, what do you think? Eventually, I'm going to squeeze dimensions out of this guy, right? Which ones do you think are the suspects for retrieving some scales? Obviously M, right? Obviously D. How about current? Yeah. Current has to depend because current is the amount of charge again you store. So it has to be related, okay, whether it's a 2D or a 1D. So it's inherently a function of geometry. So the trick is getting the dimension of the dimension out of current. Okay? So for that, what you have to know is, it turns out, so pay attention, and that's not a big deal, and you don't see it when you took calculus. Turns out, current is the integral of current density, right? It's already density, so if I multiply by the area, I get current. So current is the integral of J times dA. If you have an elemental area and you know the current density means charge per unit area, integrate over the area, then you get your current. Now, the fact that I already got a dA, I'm making progress. Remember, the whole thing I'm trying to do is get some S terms, okay? So, if I do this, I integrate j times dA, okay. If I integrate j, then I get a capital J. But, well, I integrate dA, then I get a capital A. So j times the current density times the area will give me current. Okay, that's good. So in that case, current density does not depend on the dimension. A is, of course, s squared. So it turns out I is s squared. Is a function of s squared. Did you guys realize what I did? It's just like the way calculus, remember, I mean, they start with some weird stuff, and then, okay, let's make this assumption, okay, let's map it to a different coordinate system. It's the same thing here. Current density, if you just take it by, current by itself, it's hidden, you don't see the dimension. So you go to first principle, which is, yeah, current is actually, you have current density, you integrate over an area, you get current. Now, I did that, and I found A, so I took S squared out of that. I cost S squared out. Make sense?
Another way to describe J would be like
Yeah, yes. Now you already know, okay? Once I have this, in fact, some of you are thinking ahead of running away. You already know N over D is gone, there is no S. So the only things I have are IA times IB. IA is a function of S squared. IB is also a function of S squared, so you get S to the power 4. Now, that's how you show that electromagnetic force scales with S to the power 4. Okay? So what we think, we're sitting here in 2019, March, middle of March, and we think we have discovered this. Tesla, way back when he was worried about this kind of stuff. Huh? But now it has a new relevance to us because we're trying to miniaturize things. So, another way of looking at this, if I reduce the same thing, instead of electrode, if I reduce my magnetic component by 10 times, okay? How much am I reducing the magnetic force? S squared, right? What 10 to the power 4? Reduction in electrostatic force. Electromagnetic force. So the electromagnetic force reduced tremendously, much faster, to the power 4. How about the power density? So remember, electrostatic, the power density increased by 100. How about here? It's still reduced by 100. So even if you forget everything, all the derivation, what I want you to remember is electrostatic, you reduce by 10 the dimension. The power density increases 100 times. Electromagnetics, again, you reduce the size by 10, the power density actually decreases. One goes 100 times, the other one goes down 100 times. Any question?
It says 10 to the power 4, is that right?
What?
On the slide it says 10 to the power 4.
Well, that's the electromagnetic force. It's to the power 4.
That is, okay.
Yeah. But the power density.
Okay.
Yeah, if you go back.
Yeah.
S to the power 2. Right? Okay. Now, the other ones I'm not going to derive, but I'm going to give you some examples. Those of you interested, please go and read about these things. So, for example, friction, tribology. How does it scale? So typically, friction scales with linearly or an area-wise. We know that, right? It's the contact area. Strength per weight. You could do the numbers. That scales inversely. Stiffness scales linearly. Frequency inversely. Okay, that's obvious. You reduce the size. Omar, what happens with the frequency? If you have a material, you have a beam, it has a certain frequency omega. If I reduce it by 10, or by, whatever, what do you think happens to the frequency? Is it going to vibrate faster or slower? faster, right? So the frequency increases, so that's what it's. You reduce the length, the frequency increases. That's. Now, another thing is Reynolds numbers. That contains a lot of mystery right there. That explains a lot. I was giving the same example in the other class. What was this class? Blood flow in your arteries. Is it laminar flow, turbulent flow? Anybody? Anybody which says turbulent? So it's a laminar flow, right? But if you have large pipe sizes and so on, as you increase the pipe size, you have high Reynolds numbers. Now, in microfluidics, the biggest mystery in microfluidics is when you pass liquids in a small channel, as you reduce the size, the Reynolds number also reduces in a quadratic fashion. You reduce the size 100 times, Reynolds number changes, reduces by 10 to the power 4, 10,000 times. Which means, absolutely I want you to remember this, so in microfluidics you will never have a turbulent flow. In fact, it's a big headache. It's all laminar, it's hanging out by itself, 10 Reynolds number, maximum 100 Reynolds number. In fact, if you want to mix things, it becomes a difficult. Turbulent flow is good, actually, because it mixes up things. So when you're trying to mix two liquids, you can't mix them just by having them flow or increase the velocity. So you have to create some other designs, which we're going to cover some other time. So the point I'm trying to make here is about device design, device selection, physics selection. Scaling laws have a tremendous impact. And if you pick anything from this class, it's about always going to first principles. Okay? All right, any questions? I have some weird stuff to show you and then... any questions? Okay. Now, let's look at some applications. So remember lecture number 1 where we scared a couple of people? So you guys are the brave ones who stayed. And I've done this so many times on the data. So per equation, I think I get rid of about 5 people. There are some equations with, 50, 20 people. But, I was not kidding that time because some of this requires that we understand physics. Okay, so let's talk about some of the, so when I say physics, so we're going to talk about mechanics, we're going to talk about electrostatics, okay, and then we're going to talk a little bit about microfluidics. Okay, I want to talk about mechanics. How many people have heard of F, atomic force? No? Okay, we just talked about it today. So how about SEM, standing electromagnetic?
No.
Right. So if you've heard of it, yeah. So if you want to look at small things, 50,000, 200,000 times, so essentially you shoot electrons, so that's a scanning electron microscope. But IBM, way back, I think in the 80s, in fact, the inventors are around. In fact, one of them, I didn't put his picture here, I know him. He's in UCI. A very unassuming guy, but then people invited him. He's one of the guys who created the FM, who invented the FM. So these are people who eventually get Nobel Prize about 2 years before they die, but it's okay. So what happens is, if you want to measure a surface, okay, surface profile, but it's in angstroms. So what we do is we have this device made of cantilevers with a tip. And this cantilever keeps on tapping on the surface. Okay? By itself, it's not going to read anything. So what happens is we point a laser light on top of the cantilever. As the cantilever goes and taps, and if there are features that are going up and going down, then the reflection is affected, right? So I can read, so there's a position sensor, then I can read that position. Eventually, I could map that. You cannot imagine how much difference it made in a lot of areas. Okay, it's one of the monumental inventions of our time. particularly in terms of equipment and so on, process. So this is what about, if you look at the design, so the big thing is, in terms of fabricating these, the optics is not, in fact, complicated. In fact, this thing is so easy. Professor Moon has one in his lab. He had another one built by his students. So it's not very difficult. I mean, essentially, you can buy these cantilevers, or you can make them in our lab. So the trick is that. And then light sources right now, you've seen how things are cheap right now. So you can buy this and then you can build. But and here's the physics, the description. So essentially, it's a cantilever. So this brings me to the question. And most of you guys are graduating in a couple of weeks. Fresh engineers. Some of you will be interviewed. I mean, all of you will be interviewed. So I'm sorry, I don't want to be No, all of you will be interviewed. Yeah, absolutely. But some of you will be interviewed in a weird way. That's what I want to say. So there's always going to be one cranky engineer. Probably you'll meet them after lunch. When you've forgotten everything, you think everything is going good. It's happened to me. I went to HP when I was in the industry. And I thought everything was fine, and then I met this guy. I thought I was good, but anyway. So, then they ask you stuff, questions like this. Now, for example, we have a cantilever with a load of P and length L. Those of you in my other class are always. So what's the deflection of the tip? So as engineers, okay, this is a serious matter. As engineers, you should know this, top of you. Deflection in a cantilever. Apply a load P. Length L. Young's modulus E. Moment of inertia I. So delta max. Give me a number. Give me a not number. A formula. Come on, guys. So it's going to involve any of these guys. So typically EI will be at the bottom, right? And the load should be here on the top because it's linearly proportional to the load. And then the length should be here. So PL cubed over 3AI. Please remember this number. When somebody asks you on a job interview, remember this one. Okay. So actually this guy, the way that this was designed was just this. PL cubed over 3AI. Nothing complicated. Because it's a very simple structure. Okay? Now, of course, things are not as always like this. Well, yeah, here I will show you the derivation. So it's essentially PL cubed over 3I, and the stress not big. Now, a little bit building up more of mechanics. Homework number 1. Silicon. Three planes, 100, 110, 111, depending on the way you cut it. You're going to have 3 Young's modulus, 130 typically, or 129, rounded to 130 gigapascals. 110 is about 168, 170 gigapascals, or 160, any number within that range is acceptable. 111 is the highest, so that's 190 gigapascals, okay? So, if I make a plane, now, I don't expect you to remember anything here. But this is what I expect you. Now, cantilever we covered, that was easy. What if I have a plate? So there are only 1 or 2 things I expect you to know here, so stay with me. So if I have a plate, so this is L. So this is a 2-dimensional, okay? So L here, and that's M, for example. So let's assume T over L is less than 0.1. So it's a very thin plate. Or it could be a shell. Some of you may have to design actually a shell structure, a pipe or something, okay? Or a pressurized vessel. Now, in that case, there are 2 theories. So typically, of course, nowadays, I mean, you just build a finite element model and you calculate, but anybody can do that, right? So in terms of the theories, I just want you to remember two names. Those of you interested, you can go through this. So the first one is called classical plate theory, CPT. Okay? So if your plate is very thin, you use what's called CPT, classical plate theory. Or some people call it Mendeleev, because we just want a name after people who, you know. So that's called the Mendeleev type plate. The other one is, if it turns out the thickness is very, very high, so T over L is actually much larger than 0.1, 0.3, 0.4, then we have what we call shear deformation plate here, SDPT. I mean, there are varieties, so you can call it SPT or whatever. Shear deformable or shear deformation plate here. Okay? And that is known as Timoshenko. So on an exam, if I say, okay, look, this is a Timoshenko plate, don't Google it up. You know that it's, I'm talking about a thicker plate, okay? For that, the displacements are actually much higher, okay? Because there's additional deformation. So that's what I want you to know over here. Any questions? Because I need to cover electrostatics. Any questions? No, okay. Okay, electrostatics, reason, those mirrors. And the other one is actually self-driving cars, LiDAR. Have you guys heard of LiDAR? So LiDAR, actually, we're using the same mirrors. We don't use a number of them. We usually few of these in an array format that we scan. So in fact, I think we're going to have some final design projects, LiDAR. So that essentially works with electrostatic actuation. Okay. Now, what do I need you to know in electrostatics? So electrostatics, anybody who has taken MEMS will have to know these basic theories. So stay with me on this. So once we've done this, then the rest is stuff that you can cover by yourself. Okay. So if I have two plates, separated by distance d, okay? This is V2, this is V1. Then electric field, I've given you before, but I'm going to repeat it. So it's going to be V2 minus V1 divided by D. Okay? Now, interchangeably, when we talk about electrostatics, typically we don't say voltage, we say potential. Okay? Electrostatic potential, but in short, it's potential. And potential is given typically as phi. Okay? And this quantity is scalar potential. It's a scalar quantity. Okay? It's the same voltage, the x, y, it doesn't have any direction. It's independent of direction. Okay? So, what happens is this electric field is related to V. Remember, phi is the same as V2, so I can say phi2 minus phi1 over D, which is x2 minus x1. If you were Leibniz or Isaac Newton, you see a quantity like phi2 minus phi1 divided by x2 minus x1. And you will say Eureka, and you will say, anybody? Derivative. So let's put it in a derivative form. Partial phi. Come on, guys.
Partial.
With respect to x, right? If it goes in the y direction, it could be partial phi with respect to y. That's why I'm taking a partial derivative. Okay? Now, in a vectorial form, I need you to know this. E, in fact, it was an exam in the other course. E is partial phi with respect to x plus partial phi with respect to y plus partial phi with respect to z. Now, let's do math. In a vectorial form, how does that look like? So E is partial f, partial x plus y plus z, but I can put the whole thing in a vectorial form. Anybody? The answer is on the board. Gradient of phi. It's grad phi. E is grad phi, and that's what I have. The gradient of the potential is your electric field. What if this guy is 5 volts and this is 5 volts? What's the electric field here? 0. There's no gradient. Okay. So you guys are with me on this. E is equal to grad phi.
Yeah.
But it also turns out if you take the derivative of the electric field, okay? So what do you get in vectorial form? I'm taking another gradient of grad phi. Come on, guys, you've seen it before. Fresh engineers.
Just to the power of 2, right?
Yeah?
You just put it to the power of 2. You just
Yeah, that's square phi.
Yeah, del squared phi.
So it's going to be the derivative of E with respect to, again, x and y. What do you think is that? That's typically a source, okay, the charge, okay? Q divided by K or whatever it is, okay? Now, so all I'm asking you is to know only 2 equations in electrostatics. So the first one is, given the voltage, take the gradient in x or y or z, you get the electric field. The other thing I want you to know is, how do I solve for phi? And that is given by this formula. Del squared phi is equal to Q over K, some source term. Now, sometimes you may not have a source term, just a voltage difference. Okay? Then in that case, this could reduce to del squared phi is equal to 0. So, you guys remember back in January? We had a name for these equations. Let me see your long-term method. The young man at the back, you be very quiet today. No questions? Yeah, exactly.
Right, yeah.
So the first one is Laplacian. And the next one is, if it is 0? No, if it, I'm sorry, if it's 0, it's Laplacian.
Okay, yeah, that's right.
And that one is Poisson's. Okay? Now, if you answer this question, then I'll let, we're going home. I'll let you read the thermal part. So, if I have a domain, what this guy says is, I could define phi inside, and I'm going to have some boundary conditions, it's insulated or whatever. Then I solve this equation, then I'll find out the distribution of potential. Now, let's be mathematical people. Forget physics for a moment. Same domain. Instead of electrostatic potential, think of temperature distribution. Phi is a scalar potential. T is also a scalar potential. Okay? Same thing. What kind of equation could I use to find the distribution of temperature? I'm going to ignore radiation and convection and all that, just conduction.
Does it have to put time?
No, steady state. Del squared T is equal to 0.
Those equations imply that it's a constant gradient, it's not changing.
No, the gradient would change. In fact, it's the second derivative, right? So the gradient is the first derivative. Second derivative is zero, which means non-constant.
Oh, non-zero?
Yeah. Because that's why I'm taking a second derivative. Well, yeah. I mean, the second derivative, so the addition, if you want to look at it that way, yes. There is no source term. I'm not adding potential as I'm solving.
So you're looking at it in an instant, right? Basically.
No, actually what it means is, I mean, you can see it that way, but essentially what it means is I don't have source terms.
Oh, yeah.
So I could have some guy, so for example, a heat source. So I have a boundary condition and I'm holding this to some kind of T. T is equal to 0, I isolate that, but I don't have any additional heat source. Then the conduction equation is del squared T is equal to 0. And here is what is really beautiful, because essentially the same equation applies to physics. Are you guys okay with this? If you're okay, then it will save you 2 slides.
Does this apply to concentration gradients?
Concentration gradients in terms of conservation of mass and all that. So that's complicated, right? Okay. You can forget that guy. Read this and let me know if you have questions. Cooling voltage, you guys are going to look crazy. Okay, so heat transfer. Essentially, I was going to derive the same thing here. So all I need you to know again from that is you just need to know you could solve del squared T is equal to 0, and you could solve the conduction problem. So in general, thermal problem is not only conduction, okay? Then Fletcher cannot teach any course. That's convection, right? And then radiation. But if I'm just interested in the conductive part, then I solve del squared T is equal to 0. The convective term will have a velocity u term times gradient of T. And then the radiation, if you want, you could apply it as a boundary condition. Okay? So, I'm going to leave the reading of this material to you, okay? But in terms of exams and all that, what I'm going to ask you, it's mainly dependent. It's going to depend on what I've covered, okay? Again, the point is, sum it up, scaling laws, extremely important. And I'm going to ask you a number of questions on this. So you have to understand this physics. Why does electrostatic scale favorably as compared to electromagnetics?